problems, and optimization problems are problems where you're trying to find where you're either maximizing something or minimizing something. And so it's all about finding the first derivative, sometimes using the second derivative to see whether you're at a maximum or a minimum. And some of these you have to do graphically, and sometimes you don't have to do them graphically. Okay? So it gives you some strategies in the book for how you go about solving these. So the first thing they say is understand the problem. So read the problem and figure out what you need to do. So you don't want to be maximizing the volume of something when they give you the volume, or they're asking you to minimize the surface area. So if you're like building a rocket and you want to hold your volume constant and minimize the surface area in a cylindrical shape, what dimensions would you use and stuff like that. Okay? So you need to understand what you're trying to answer in the problem. And then once you understand that, you have to develop a mathematical model, and sometimes a lot of times that involves drawing pictures and labeling the parts that are important, introducing a variable, and then you have to solve an equation, usually in terms of one variable, in order to solve the problem. So a lot of times you'll be given two equations with two variables, and a lot of times what you have to do is get the equation into, so you'll have one equation with two variables, another equation with two variables. So a lot of times what you'll have to do is solve one of the equations for one of the variables and plug it back into the other equation. You probably did this in pre-calculus as a preview to doing that, like when you try to find the volume of a box and then you use your calculator, the best dimensions to maximize the volume or surface area or something, and then use your calculator to do that. Well, now you have calculus, so you can use calculus to figure out how to optimize these functions.
Is that why they call it calculus? Because you can do it without a calculator?
No, I think calculus means change. Okay? Calculus means it's all about how things change. So graph the function, and so then they tell you to graph the function, find the domain of the function, determine the x values and variables. To determine the x values that make sense. So a lot of times you will get an answer to a problem that doesn't make sense, and you have to throw away that answer. You'll see that in a couple problems. And so you have to pay attention to the domain of the function, as in, you'll see, okay? Identify the critical points and endpoints. So usually you have to, if you're trying to maximize or minimize something, you got to make sure, like if it's a cubic function, you might find a relative maximum over here, but this might be the true maximum. So you have to look at the endpoints to see what's happening at that function, okay? And then solve the mathematical model to ensure, if unsure, the results before you confirm. So that means solve it algebraically using calculus, and solve it maybe to looking at your calculator, okay? And then interpret the solution, translate your solution result into the problem setting, and decide what result makes sense. So for instance, on that last test, it said, what does the rate of change mean? Interpret the rate of change. And a lot of you had picked up a point because you said the rate of change is this. All right, that's not what I'm looking for. It was like the rate of change was like negative 1.9 or something, which meant that, and you have to look at the units and everything, it meant that the attendance at a movie is going down by 1,900 people per day after 4 months. That's specifically what I was looking for in that problem, okay? Because you have to interpret, you're using calculus to solve a real problem. You have to come up with an answer that makes sense, all right? And same thing with, like on an AP test, I'll do that at the same time. So anyway, here's the problem. This is a pretty easy one. Find two numbers whose sum is 20 and whose product is as large as possible. So, do you understand the problem? Go like this. Yes, we understand.
Yes.
Okay. So find two numbers whose, this might be an ACT problem, which you could solve with your calculator. It's quicker. Well, maybe quicker with calculus, but two numbers whose sum is 20 and whose product is
10.
What?
Let's go.
10 and 10.
because those are sick numbers.
Those are sick. But to use calculus, what do you know about x plus y?
Yeah, you're right.
X plus y? What are those? Those have to add up to, x plus y have to add up to 20, and x times y, that's going to be the product, okay? So that's the product. So what I usually want to do is solve these for one equation in terms of another in order to get a equation with one variable in it, or with one independent and one dependent variable. So how could I do that in this case? What do I solve for over here and substitute in here?
X equals 20 minus y.
Yeah, I like x better, but you could write y equals 20 minus x. Same difference. It'll work out the same. Y, but we've been taking derivatives with respect to x, so let's just do that. Otherwise, we'll confuse people. So y equals 20 minus x. Yeah? And then you take that and you plug it in here, and then you get x times 20 minus x equals the product. All right? And now I'm going to solve that and see what well, first I want to take the derivative. All right? And I would just multiply. So a lot of people, you could use the product rule, but that's kind of a pain. So what I want to do is multiply this out first. So 20x minus x squared equals the product. And then I could just take the derivative of that. So p prime equals what? 20 minus 2x. And then when the derivative is either undefined or 0, you can find critical values, right? So we're finding critical values. So you set the derivative equal to 0, because there's no place that this is undefined. And then I will solve this. So I get 20 equals 2x, so x equals 10. But this doesn't answer the problem, okay? Because that might be where the product is at a minimum. Okay, I'm not sure, but you should do a second test to make sure. So you could either do the first derivative test, where I draw a line and I go to the left of 10 and the right of 10. So you look at the derivative. To the left of 10, so like if I plug in negative 11 in here, what kind of number would I get out? I'd get out a negative number, right? Whoops, like 9, I'm sorry. Oh wait, that's wrong. If I plugged in a number to the left of 10, like 9, what kind of number would I get out?
2.
A positive number. Okay, if I plugged in a number to the right of 10, like 11, what kind of number would I get out? Negative. So that means that my function is going from sloping upwards to downwards. So what do I have at that point? I have a relative maximum. Okay? I have a, what? I'm writing things in. Relative max. Now the other thing you could have done is done the second derivative test, p double prime. What's p double prime equal?
Minus 2.
Minus 2. So if my second derivative is negative, okay, which it always is, then that means it's concave down, which means you're at a maximum, right? If the second derivative, so since the second derivative is negative, that means that my function is always concave down, okay? So I know that's something that the slope is 0 at 10, okay? So it's always concave down. And so using the second derivative test, I could also confirm that you're a maximum, okay? Interpret the solution. X is 10, what's y?
2.
Y equals x plus y equals 20, so what's y? Hello, 10, right? So two numbers whose product is a maximum, and they add to 20 would be 10 and 10. All right? You could try some other numbers like 3 and 17, get numbers smaller than, okay? And it won't always be, where it's that easy and straightforward, okay? So let's move on to the next type of problem. So this is a trickier one. Okay, so I stole these from the book. So, and this is pretty confusing, but maybe it's confusing, but maybe not. But a rectangle is to be inscribed under one arch of a sine curve. There it is. That's what the rectangle looks like. What is the largest area of the rectangle and have what gives the dimensions of the area? So if this is a sine curve, one arch of a sine curve, what would this point be? 0. Let's just do the first arch of the sine curve, okay? So you could use other arches, but this is the better arch, right? So what would this point be in a sine curve? Pi. Do you guys understand that? All right, because sine goes from 0 to 2 pi. All right? And then this point right here, we're going to call, I think they call this point x. And so this point up here is going to be x, comma, what? Whoops, x, comma, not x. X, comma, what? How do I find the y value if this is a sine curve? X sine x, very good. So that's the point x, comma, sine of x. Would you agree with me there? Yeah? Okay.
Yeah.
Now this point is a little trickier, but you can find it by going pi minus x. No?
Yeah.
Yeah? Okay. So if this is pi to here and x to here, then this distance from here to here is going to be pi minus x. So this point over here is going to be pi minus x, comma, sine of, comma, sine of pi minus x. All right? Yeah? Okay. And then, but that's not really the dimensions of the rectangle. What is this dimension from here to here? How would I figure that out? Kind of weird, but you can do it. If this is the point, if this x value is pi minus x, and this point is x, how could I find the length from here to here?
Pi minus 2x.
Oh, is that right? Yes, yes, pi minus x, b minus a, right? Pi minus x minus x, right? To find this length right here is going to be pi, who said that? Connor, okay? Pi minus 2x is, pi minus 2x is the width of this rectangle. Yeah? Yeah? No? Amy? What's the height of this rectangle? Sine of x, or sine of pi minus x, which I think would be the same, right? It's going to be symmetric on both sides, right? So I think that if you plug in sine of, aha! How was the picture? How am I finding the height again, David asks? Well, it's just I plug in x in here, right? So the y value is just going to be sine. This is a sine function, right? So the dimensions of this rectangle, the area is going to be pi, the area, not area times, the area, which is a thing that I'm trying to optimize, okay, is equal to pi minus 2x, which is the width, times the height, which is sine of x. You got that? And now what you have to find, you don't understand that?
In one case, the height is sine of x. In the other case, it's sine pi minus x.
Yeah, but those are exactly the same. Okay? They're exactly the same because pi is periodic. So sine, and because it's a rectangle, it's going to be, yeah, symmetric. Okay? Because that's kind of inscribed under one arch. What is the largest area? Okay, so those are, yeah, those would be, they would be the same if it's a rectangle, right? If it's a rectangle, then they're going to have to be the same, right? Okay, so then we're going to find the derivative of the area, because that's the thing that we're trying to maximize. dA dx, okay, or a prime with respect to x, and then you have to, how can I do that? I have to apply the product rule, right? So that's going to be, should we take the derivative of the first thing first?
Yeah.
Okay, so what's the derivative of the first thing? -2 times sine of x, right? Plus pi minus 2x times what? Cosine of x, okay? And then you want to see where that thing is equal to 0. Well, in this case, you can't really solve that algebraically. I tried to and it didn't work, okay? And so at some point you say, okay, I'm done, there's nothing else I can do. I don't think you could really, what I tried to do, I set this equal to 0. I said -2 sine of x. And then I distributed this and I ended up getting tangent of x by dividing sine by cosine, but it didn't really do me any good anyway. So then at that point, what you want to do is say, okay, I'm done. I'm going to use my calculator and see where the derivative is equal to 0. Okay? And so, yeah, you wrap it. All right? I mean, if you could solve it algebraically, that's the ideal thing to do. But in this case, you cannot solve it algebraically. So we're going to go to my calculator and you might say, well, why not just plug the original function into my calculator and find the maximum? You could do that too, but that's kind of, they want you to do some calculus here, okay? So y equals, I'm going to go to y equals, I'm going to go view always in front, otherwise it'll disappear. And you got to make sure you're in radian mode. Am I in radian mode? I'm in radian mode. And I'm going to plug in that function to the best of my ability and see if I mess up. So -2, and there's no reason to really mess with it. Stop doing that, please. Sine of x. I'm going to say your name on the loudspeaker, and then you'll be right. I'll send it to your parents. Plus second pi minus 2x times cosine of x, like that, okay? And then, what club?
Grill club.
Grill club.
Yeah.
Boy, you are just in every club there is.
That's not
Grill
real
club.
club.
That's the grill club.
That's not
They
real
grill-
club.
grill.
Every Thursday, they go
Thursday.
during summer period. They go out and grill.
No,
Oh,
it's
that sounds
second
fun.
lunch.
Okay. All right. So anyway, let's make sure that your window makes sense. So, what? Did I mess up? So make sure your window makes sense. So I would, since the values that make sense for x are only going to be between 0 and pi, I could set up my window right away for that. So I'm going to go between 0 and pi for my second pi. Does that work? There I go. And then for my x-min, since this is always going to be a positive value, right? According, and sine is positive between 0 and pi. And so the sine of x is going to be a positive number between 0 and what? What is the highest that sine goes? 1. So I'm gonna,
Pi.
But it's the derivative.
it's the,
Oh,
we're finding the area,
I
right?
was saying pi over 1.
Yeah,
too.
so you
Yeah.
don't want,
So,
you don't necessarily
so
want-
1 times pi is, so the biggest it's going to, so this is where you have to think about your domain and your range and stuff, okay? So the domain, the biggest x is ever going to get is pi. But y could get to be, since sine fluctuates between -1 and 1, and you think about pi times 1 is what? What's pi times 1? Pi. So the biggest y is ever going to be able to be, I think, oh, maybe not. minus 2 sine x. Let's just see what happens if I plug in 6 in there. Let's hit graph, okay? And see what I get. And there I get this function, and
So did you plug in the derivative or did you?
I plugged in the derivative, okay?
Can we see what you typed in?
Minus 2 times sine x plus.
Yeah, so I'm gonna change my window. So I plugged in y equals, I plugged in the derivative function, okay?
Yeah.
Oh yeah, so that doesn't make sense if I were to plug in, my window, so I have to think about the window for my derivative, not for my original function, right? Okay, and so I'm going to go down a little more. That window didn't work, so I'm going to make it go down a little bit more, maybe say the y min.
If you do negative 3, you'll be good. You already passed y min.
Y min, thank you. Negative 3 would work?
Yeah.
There it is.
Negative 3, and then if I hit graph, you can see that this is a graph of the area, okay? And then you could figure out that this part in here, you're trying to find out the, so in this case, hold on a second, view, always in front. Okay, can I write on here now? Write on here. Oh, they won't let me write on here. What's true about the derivative here?
Positive.
Positive to negative, right? So what do I have at this point right here? I have a maximum area, right? What's true about here?
Yeah.
Negative to positive, so I'm at a minimum. And anyway, the area can't be negative, right? And so none of this stuff is.
No, but that's not the area.
Oh, that's not the area. You're right. Yeah, you're right. This is the slope of the area, right? Of the area function. But anyway, you can't get it from seeing that the slope goes from positive to negative here, and then you're going to go to second calc. Okay, second calc. Whatever. Second calc. And you're going to look for the 0. Got it? I'm going to hit enter, and it's going to say left bound, and you want to go over to before it crosses the x-axis. Okay?
So it's where the positive crosses over to the negative,
Yes.
not the other way around.
Right, because this is a graph of the slope of the curve, right? So the slope is going from uphill to downhill. So if this is a graph of the original function, which does, I think the original function, it goes up and down like that, right, Connor? If this is, you're looking for where the slope goes from positive to negative. And at this point, the slope is going from positive to negative. So left bound, I hit enter. Right bound, I go over to the right side of the curve. Okay? I go below the line. I hit enter. Okay? And I hit enter, and then it'll say guess. And you guess. And it tells you that that point is about 0.71. And you want to take these answers to 3 decimal places, okay? For my class and for an AP test. You want
So
to-
that point right there is where
Yes.
that
X
graph in
equals
green.
X 0.710. Yes, that point says that when X is about 0.71, which is, this would be half of pi, right? So this would be pi over 2 right there. So that would be about 1.5 something, right? So 0.7 somewhere in between, kind of in the middle somewhere. Maybe it is exactly in the middle. Is that pi over 4? I don't know. Is that pi over 4?
5/4 is 0.7.
It's a little less than pi.
It's a little bit less. So there is a place where the graph, so X is 0.71, and then always answer the question, okay? What dimensions give you the area? And so the second thing is to find out the y value, and the y value is sine of 0.710. And if I plug that into my calculator, right, because this is x and this is y in that rectangle. If I'm finding this is this is width and this is height or something, that rectangle. And so sine of that, if you plug that into your calculator, you get out sine of should be more accurate. What do we have? 0.714 or something like that?
7104.
7104. Okay. We'll just call it 7104. Okay. And then if I hit enter, I get that value is about 0.652. So about
radians or degrees?
652. That's in, that doesn't, they don't give any units on this. So I guess they might give you inches or they might give you radians, I guess. Yeah, radians. So that would be radians squared. So the area is going to be, they don't ask about there, but if I want to find the maximum area that you can put under that sine curve, it would be that. All right?
So you
What?
have
They do ask.
Oh, they do ask you?
What is the largest?
What is the largest area? So you would multiply those out, and I think you get like 1.2 something or something like that
Isn't it pi minus 2x, not just x?
for the width.
Because when you put your
Oh!
down there.
Yes, but I think it comes out to be the same, doesn't it? X, so pi,
I don't think so.
oh, thank you, Braden.
You're welcome.
Pi minus 2, pi minus 2 times 0.710. I screwed up. Okay, so that is equal to, I did this, I should look at my notes, and so that I'm not, so if I do that, I get out 1.72. I'm sorry. So this comes out to be, this is wrong. Okay, the area is pi minus 2x, which is 1.72 times sine, I really messed up. I better re-record this video. Times sine of 1.72.
No, I think the sign is the sign of x, isn't it?
Yeah, it's the same anyway, okay? Which comes out to be 0.652. And then if I multiply those two together, I get approximately 1.12. Okay?
Wait, what just happened?
I messed up because I put in x instead of, the width is pi minus 2x, right? Not x. So I messed up, so I have to find out the width and the length. So I'm not trying to find x, I'm trying to find out the width. So that's a good example.
X is still 0.710.
X is still 1.710.
Yeah, x is
But
the same.
pi minus 2x here is 1.72, right? And that's what goes into finding the area.
Okay.
So that's another, obvious reason you want to, in geometry, but I think we did this if you were in geometry class, we put up a box and we tried to find the volume that would give you the maximum volume in that box. Watch, I could even do this with my special drawing tool. I'm going to make a box. Here's a box, okay? And I'm going to cut out the corners of this box by putting in little squares over here. So here is, I'm going to cut these corners out. Here and here. Am I recording? Yeah, I'm recording. So I'm going to cut these things out, and this is why you really have to draw a picture of the situation. And you cut it out of a 20 by 25 sheet of paper. So here, from here to here is 20, right? And here to here is 25. And you go like that. And then you call this piece X, and you call this piece X, and this is 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 X. Okay, so then what you want to do is fold it up, right? When you fold it up into okay, I'm doing as well as I can here, preamps. But when I fold this box up, okay, this side is going to be what? What's this side going to be? Yeah, one of them, the shorter side, will be 20 minus 2x. Do you guys see where that comes from?
Yeah.
Right? And the other side is going to be what?
25.
25 minus 2x. And what's this going to be? X. Everyone understand where that comes from? When you fold it up, that's what you get. You fold it up at the corners. So then, look at what the question is asking you. How large should the squares be to make the box hold as much as possible? So what are they asking you to maximize? The volume. And to find the volume of this box, okay, I go 20 minus 2x times 25 minus 2x times x. And I could FOIL that. And first I'm going to FOIL this part. We're going to do this algebraically. Okay, so we're going to try to find the maximum.
So you could just plug that right into your calculator?
Yeah, but if it was a non-calculator problem, which it could be, you would be expected to take the derivative, see where the derivative is equal to 0, and then figure out if you're at a maximum or minimum. And once you have your answer, you have to make sure that your answer is within the domain of your function. Yes, sir?
How do you know that x is the third variable?
Because if I fold this up, right? If I fold it up, right? I fold along this dotted line, and I fold along this dotted line, okay? Then it's going to have a height of x. See, you get that? There's it. So this ends up being the side, right? But these are really good geometry problems. So if I follow this out, 20 times 25, is that 500? I think it is, okay? You get 500, and this times this makes minus 50x, and this times this gives you minus 40x. So minus 90x's altogether. Tell me if I make a mistake, because I once made a mistake when I was doing math. Okay? Minus 2x times minus 2x makes plus 4x squared. Okay? And then you have to multiply all that by x. And I'm going to, so still I'm finding my volume equation, which is I'm going to bring the 4x cubed in front. Okay? Minus 90x squared plus 500x squared, thank you, plus 500x, and then I'm going to take the first derivative of that, okay? So the volume is 12x squared minus 180x plus 500, and I set that equal to 0. Okay? And then you could use the quadratic formula, or you could try to factor, which I don't think it does factor. I don't think 12, does 12 go in here? Does 12 go into 500?
Does 12 go into 50?
Yes, I think it does.
No, it doesn't.
Yes.
No, yeah, but. So then what you have to do is use 5. So this is, I guess you're kind of using your calculator, but you can do this on a non-graphing calculator, okay? By quadratic formula, you get out 2 answers. And this is kind of important. You get x is equal to, about equal to, okay? By quad form, you know the quadratic formula, right? X is about equal to 3.681. 3.681, or x is about equal to 11.317. Okay? Now, something's wrong with that. Who can tell me what's wrong with, why can I throw away one of these answers?
Because it is not the right answer.
Why is it impossible? It's not in the domain. Because see this, going back up here, right? Looking at my box, okay? This side is 20 minus 2x, right? 20 minus 2x.
Yeah.
What about 20 minus 2x? What does it have to be bigger than? This guy can't be negative, right? Can't be 0 or you wouldn't have a box. So 20 minus 2x has to be bigger than 0. So you solve this little inequality, minus 2x has got to be greater than negative 20. Divide both sides by negative 2 gives you x has got to be less than 10, right? So this one you throw away because it's not in domain. You see? Okay? And then so all you have to do is check this one to make sure it's a maximum and not a minimum. What's a really quick way to check if it's a maximum, not a minimum?
On the second derivative.
Take the second derivative, which is easy to take. So whoops, that should say v prime, right? So what's v double prime? Equals 24x minus 180, right? And so you get, so you don't have to set it equal to 0 or anything. All you have to do is take this and plug it into here and see what kind of x, what kind of number. I'll be right there. Give me like 3 more minutes. Okay? So all you're going to do is plug this number in here. And 4 times 24, I'm just going to kind of do this in my head. 4 times 24 is 96, right? So 4 times 96 will give you a number less than 0. So 3 times 3.61 is going to give you a number less than 0, which means that v double prime at that point, v double prime of 3.681 is negative, which means what? Concave up or concave down? Concave down, which means that I'm at a maximum for my volume. Okay? And then the other thing, the other thing you should also check is checking at the endpoints too, right? To see, because this is a cubic function, so it's going up and down like that. But obviously, if you made this number 0, then I know we need to go. I'm just gonna put up the homework up here, and you guys, I have one more problem each. If I don't get it into this class, it's about a cylinder. You can look at the example I'm going to put on and go through. Oh, not done yet, because you have to plug in that x value and figure out the dimensions of the box, right? Because still you have to take that 3.681, plug it in, and get those dimensions. All right? So I'm very organized today. See, this is the next one, and I will, if I come back in time, I'll do that one. If I don't, you can start on these problems. What does that say?
2,000.
2,000. I think that should say page 233. Okay? So you can go back to where?
The cylinder.
The cylinder, that's in your book, okay? So,
It's an even sample process.
but in this one, you're trying to minimize something. So this is tricky algebraically, so I wanted to get through this one. So if I don't do it with you guys, because I gotta go to the ball sports club, I'll do it on my video and you can watch it, okay? So anyway, so your homework is this. You can start on that. I'm gonna stop my video. And, start my recording again. This is gonna be a really long video. You have been asked to design a 1 liter oil can shaped like a right circular cylinder. What dimensions will you use? So one of the tricks here, this is R, this is H. And so you're trying to minimize the surface area with a given amount of volume. You understand that? Okay, because it gives you, it says design a 1 liter. This is kind of hidden in the problem, but it's a 1 liter oil can. Okay, and 1 liter, that's me. Okay, 1 liter is equal to 1,000 centimeters cubed, right? I think that's what it is. Okay, do you know my Aunt Millie?
We don't.
You don't know milliliter?
Yeah.
She's not very big. That's a, no, a milliliter is the same as a cubic centimeter, I believe. Yeah. So 1 liter is 1,000 cubic centimeters or 1,000 milliliters. All right. And so, but you also know that the volume. So you have 2 equations. The volume. Anyone remember from geometry? I told you this in the last problem. Pi r squared h, right? Surface area, which is the thing that you're trying to minimize, And in this case, you have one in your homework that doesn't have a top. So the only difference between the one you have in your homework and this one is that this one has a top and a bottom. Okay? So the surface area is going to be 2 pi r squared, because you have a top and a bottom, right? Plus, does anyone remember the formula for the surface area of a cylinder? It's the circumference times the height. Remember that? 2 pi r h. So you have to know some geometry to do this. All right? So what you're trying to do is minimize this thing. And before you can do that, you have to have an equation in terms of one variable, or a surface area in terms of either r or h. And so you could solve this equation for either r squared or h, right? But this is 1,000 over here, right? 1,000. So in the book, and the way I did it, and that's not to say that's the only way you can do it, you get that h is equal to 1,000 divided by pi r squared. You can also solve for r squared. Oh, you don't want to do that because then you have to take the square root of it and plug it in here, and it's going to look ugly. So you take your h and you plug that in to this equation, okay, for h. And what that gives you, now you have an equation just in terms of the radius. So surface area is 2 pi r squared plus 2 pi r times 1,000 over pi r squared, right? Did that right? Did that right? And then this pi goes away with this pi. Yes? I'm doing this right.
One of the R's goes away too on the bottom.
And one of the r's goes away. So this r goes away with one of these r's. So when you rewrite this simplified, you get surface area equals 2 pi r squared plus 2 times 1,000 makes 2,000.
Yeah, it's over R.
Yeah, but there's a 2 out here, right? So 2 times 1,000, 2,000 over r. Let me double check to make sure I did that right. I did, yes.
That surface area right there is saying, like, the different amounts of surface area that you could use and they'll all hold 1,000.
They will all hold 1,000. And what you're trying to do is minimize the surface area. Because maybe you're an engineer and you want to eliminate your costs of your product that will hold the same amount, right? So if you're out, building oil containers or rocket ships or something like that, you want to use the least amount of material possible, okay? So then I want to minimize that, so what do I need to do? Take the what? Derivative. So you're going to take ds, let's call it dr, okay? The derivative of the area with respect to the radius, and you get 4 pi r. 4 pi r. This is r to the -1, so this derivative is negative 2,000 over r squared. Do you understand that?
Yeah.
Okay, what I did? And then, probably the best way to do this, you want to see where this is equal to 0. What I would do is find a common denominator. So dr is equal to, I'm going to multiply this by r squared over r squared. 4 pi r squared minus 2,000, the whole thing, over r squared. Okay?
That should be
Pi r cubed. Where is, r cubed, you're right. 4 pi r cubed. And so what you want to do is see where this derivative is either undefined or 0, right? Undefined doesn't help you because what's your radius going to be? The radius is going to be undefined when r equals 0, but that doesn't make
can't
that,
have a negative
yeah, you
zero.
can't have a 0 radius, right? So that's not in the domain of my function, okay? So I'm just going to look at where the top is equal to 0. So 4 pi r squared equals 2,000. Yeah? 4 pi r cubed, thank you. 4 pi r cubed equals 2,000. So r is equal to the cube root of 2,000 over 4 pi. Follow that?
Yeah.
Okay. And then you want to see what the r value is at that point, and you get that it is approximately equal to 5.419. Okay, I looked in the book. 5.419. And you want to make sure that you're at a minimum at that point and not at a maximum. So one way you do that is by plugging in a value to the left and the right of that point. So if I plug in a left to the left of 4 point something, this number is going to be a negative number because this is always positive, right? And 5.419 is where it's 0, right? And so if I plug in a number to the left, you could do the second derivative test too, but I don't want to take the second derivative of that. I could. Let's just do that. dA squared, let's just do that. D squared A, second derivative, over dr squared. It's not that bad. It's just 4 pi minus, or plus now, because this is r to the negative 2. I'm going to skip some steps here. So that becomes plus 4,000 over r cubed. When this number is 5.49, is this quantity positive or negative? Positive. So this is positive, and so that means that I must be at 5.49. It's concave up, which must mean that I'm at a what? Minimum. So that's a relative minimum at 5.419. And then you have to make sure that that answer makes sense. It says what dimensions will use the least material. If you take that 5.419 and you plug it in here, you get out about 10.8 something. So it turns out that's 10.88 or something like that. So the dimensions are, it's basically that this one is double the other one, is what it comes out to be. And somehow in your book they show algebraically that this is equal to double this, and I couldn't figure out for the life of me how they figured out that 2r is equal to h algebraically. They said with algebra we show that this is this, and I couldn't figure out. I was looking at it. Maybe Terry could figure it out. Okay.
So
But basically,
are you sure that the answer to the cube root of 2,000 over 4 pi
yes,
is 5.419?
yeah. It's. I think that's what the book got. Okay.
What did I do wrong here?
5.419. I'll look. Okay, so I'm gonna pause, and your homework is.